Magic Hexagon is a simple but challenging Sudoku-like puzzle dating to the late 19th century. Today, we're going to try our hand at solving it. The puzzle consists of this 19-cell hex grid. The goal is to label it with unique, consecutive integers from 1 to 19. Simple enough, right? The catch is that each of the 15 rows must sum to m, the magic constant. Time out. Before I continue, feel free to pause this video and give this puzzle a shot for yourself. I must warn you though, it's harder than it looks. It took one guy 47 years to solve by hand. Anyway, back to the solution. First, we need to figure out the value of m, the magic constant. Note that adding up all the cells should give us the sum of the first 19 non-zero integers. Since this is 5 rows, we know that it must equal 5 times m. The right-hand side is a simple arithmetic series with a known formula. So evaluating, we get 190. Now, dividing both sides by 5, we find that the magic constant is 38. Now that we found the magic constant, we can proceed. If you're like me, your first instinct is to brute force this problem by generating all possible solutions and then checking them. The good news is since there's only 19 numbers, there's only 19 factorial possible solutions to check. Okay, this is totally not going to work. That's almost 122 quadrillion permutations, which is way too many for my computer to get through. On the bright side, we don't have to do anywhere near this much work. Here's why. Consider this random permutation, for example. Since the first row doesn't add to 38, we know that this permutation is bad. But we also know that any permutation starting with these three numbers, 13, 1, and 11, must be bad. So we don't even need to bother checking them. In the context of search algorithms, using tricks like this to rule out possibilities before you even get to them is aptly named branch pruning. In order to help our algorithm run in a reasonable time frame, we'll want to prune as much as possible as soon as possible. With this in mind, the most intuitive algorithm for us to use is called a depth-first search. It's kind of like exploring a maze. You go deeper and deeper until you hit a dead end, and then you backtrack to the last fork and choose a different path. For our puzzle, here's what that'll look like. We'll start with the first cell. We could put any number here, so we'll go in order, starting with 1. In the second cell, we again can pick any number from 2 to 19. We'll choose the smallest one, 2. Since the top row must add to 38, however, we know that the third number must be 35, and since we don't have 35, we've reached an impossibility, and so we can backtrack. We'll pull the 2 out of the second cell and replace it with the next smallest number, 3. Now we know that the third cell must have a 34, which is still impossible. Continuing like this, we'll eventually try putting 18 in the second cell. Now the third cell must be 19, which is available, so we'll put it there. We'll continue clockwise like this around the edge. Note that starting with the edge allows us to prune branches as early as possible, since the edge rows have only 3 cells instead of 4 or 5. Hopefully you're starting to see a pattern. We'll continue to work our way around the edge, rejecting 3 and rejecting 4. But we'll find that 5 works, since we do have 16 available for the third cell. Skipping ahead a bit, we'll reach this point. We've already rejected 3, 4, 6, and 8, so we'll try a 9 here. Putting 14 in the third cell, we now see that the final number in the outer ring must be 24. Since this is unavailable, we can reject the 14. There are no other options for this cell, so we'll have to reject the 9 as well, and the search will continue. Eventually, we'll reach a stage like this, allowing us to complete the outer ring. And of course, given our method of construction, all 5 magic sums are satisfied. Great, now we know how to find valid outer rings. If we code up this algorithm and run it, we'll find that there are only 30,504 such rings. Well, that's not so bad. Anyway, back to the example. At this point, solving the rest of the magic hexagon is fairly straightforward. We'll start by picking the smallest available value for the first cell in the inner ring. Now we can calculate the numbers necessary to fulfill all the magic sums. Since not all these numbers are available, we can reject the 1 and try the 2 instead. Once again, we don't have a -1 or 13, so we'll reject the 2. Skipping ahead a bit, we'll try the 7. Now all the necessary numbers are actually available, so we can place them in their appropriate cells. Note that the 5 3-cell magic sums are of course still satisfied. But now the 6 4-cell magic sums are also satisfied. And finally, so are the 3 5-cell magic sums. That's all 15. At this point, we've found a valid solution to the magic hexagon. But are there others? Let's code up the rest of the algorithm. We'll try running the whole thing, which should find every possible solution. And, well, there they are. All 12 of them. Notice that our hexagon, however, can be rotated in 6 ways. Plus, each rotation can be mirrored, giving us a total of 12 possible orientations for the same permutation. If we do a bit of inspection then, we'll find that each of the 12 solution amounts to a different orientation of the first one, which we found earlier.
Now, it is possible for us to actually ignore these duplicate orientations while searching, which could reduce our algorithm's runtime by up to 12x. And there's plenty of other optimizations we could try as well. But frankly, why bother? Even though our algorithm is written in Python, which isn't particularly fast, because of our pruning-based approach, it still runs in under a second.
So there we go, we've solved the magic hexagon. For more information, including a mathematical proof for why this is the only solution, check out this Wikipedia page. There's also this fascinating essay with information about the history of the puzzle and alternative solution methods.
Well, that's all for today. All the code used for animating and solving this puzzle is linked in the description. Thanks for watching. Let me know what you think in the comments, and happy puzzling.